Hi there, welcome back to Petrophysics Rocks. This is the second chapter of my Petrophysics for Dummies series. This one's called Lithology, how we determine what rock types we encounter. When we drill holes in the reservoir, down to the reservoir, we normally mash up the drill bit. You know, the drill bit fractures all the rock into little tiny cuttings, but occasionally we take big bits of core out. We can actually look at the rock and see what sort of reservoir quality we have. This rock's from 13,212 feet below the seabed. That's quite a bit. But as you see, we can take it out. This is quite a small core, actually, handy for YouTube videos. And you can see here what all the rocks are: sandstone. Not much shale in this one, or a little bit of muddy stuff here, but hopefully, if you watch the second chapter of the Petrophysics for Dummies course, you'll have a little bit more of a clue how we tell the rocks up. Remember, if you can like and subscribe, that would all be much appreciated. Cheers, then. So let's get on with it. The first presentation, second slide, second chapter. Here we go.
Here is a section of rock in our reservoir. Remember, we've got the mud rocks on the top, some sandstone rocks here. I've put in some carbonate, a little bit more sandstone, and then we drill down into some basement rocks or some granite. So, what measurements do we make? What measurements can we make when we drill holes in this type of setup? Well, we can drill into the reservoir, and then we can stop, change our drill bit, and then we can go in with a device called a corer, and we can take some core. We can actually take some of the rock from the reservoir in a core, long cylinder of rock, and actually remove it, take it out of the reservoir, put it into the laboratory, and have a look at it under a microscope, and maybe even lay it out on a table and see what types of rocks we've got quite directly. So coring, we recover it to surface, we can make a description and run some analysis on it. Here is the same piece of core. These images here on the left hand side are under normal white light, and you can see that this rock here is actually sandstone, and it's stained dark with black oil. And these rocks here are the mud rocks, and you see that the oil stays between the mud rocks and the reservoir. And here is exactly the same interval of rock laid out on a table with a photograph under UV, ultraviolet light. And under ultraviolet light, oil and hydrocarbons tends to fluoresce and glows quite, and this is quite a nice, pretty golden color. So that's what pays the bill. This is oil filled sandstone, and that's why it's glowing here. And these shales, these mud rocks, which don't contain any oil, appear quite dark. So we can measure petrophysical properties directly on these. So these little holes here are what we call plugs, core plugs, that we take out of the reservoir, take out of the core, and make measurements on. So we can measure that porosity. In some cases we can even measure directly the amount of fluid that's in there. So we can tell a lot about the reservoir from the core data. We can get an understanding of the sedimentology, that's the geology, understanding, looking at these rocks. A geologist can say, oh yes, this was deposited in a swamp, or this was deposited deep under the sea, or it's deposited by a river. Once you have that sort of understanding, you can start to predict, well, if that's the type of sandstone rocks here, where might they best exist in your reservoir? We can also make measurements on here about the hardness and the mechanical properties of these rocks, and that helps us in understanding how best to drill them in future. And also we can test out various chemicals on the rocks. We can see how they react with various chemicals that we might put in during the course of an oil field's life, to see how they react. Sometimes if you put some particular chemicals in the reservoir, the the shales or the mud rocks can swell up and react quite badly and start to collapse your well bores. And other times, chemical reactions in the rocks that you want to stop, such as scaling or whatever, you might want to put some chemicals in to stop your downhole reservoir scaling up. And so you need to know how they're going to react with the rocks. So that's coring, a direct measurement, but as you can see, it's not really practical to core all of our rock. You can only get quite small sections of it. It's quite an expensive business to drill into a reservoir, stop, cut a core, come out, go back in and cut another core. So often we just cut a few cores and we get some direct measurement detail from that. But generally, we have to do some other types of measurement. So getting back to the first element of the things we need to know in our petrophysical world, we need to understand the rock type. So in addition to coring, what we can do is drill wells into our reservoir. And here is a well going down into our stack of rock, and we need to make a measurement. These are those tools that I showed you right at the beginning. Put these tools into our reservoir and make some measurements, and from those measurements we can determine what rock types exist in our reservoir. And we can do this over a much broader range, over a much larger range than we can afford to take cores in. So we can log maybe 3 or 4 or 5,000 feet of reservoir interval, and that's obviously much more cost effective than cutting solid cores of rock out, which typically we cut from between 30 to 90 to maybe 180 feet at a time. But here, with wireline logs, we can log much larger intervals. So this first type of measurement is one of the simplest measurements we make just to determine rock type. And it's called gamma ray logging. Now what we see, a gamma ray is a passive device. That is, it listens to the formation. Okay, so it doesn't do anything to the rock itself, it just is a measurement device. We put down the hole and it listens, if you like, to the signals given off by the reservoir. Now naturally rocks contain naturally occurring radioactive elements, thorium, potassium and uranium, and they all emit gamma rays. So all around us, in fact, rocks are emitting these gamma rays, and if you listen for them and if you measure them, you can see them. Clays and mud rocks have a much higher thorium and potassium content, and they give a high gamma ray response. The carbonate rocks are usually less radioactive than clastic sands, so they generally have a bit of a cleaner response. Igneous and volcanic metamorphic rocks can have all sorts of exotic mineralogy, and so they can often have quite high radioactivity themselves. So what we do with our tool is we put the tool down the hole on the end of a wire line, and we pull it out slowly, and as we pull it out, a measurement is made. And here what I've shown is that the increasing radioactivity comes from left to right. So over here we have higher radioactivity, and remember the mud rocks and the clays, they all contain higher content of thorium, potassium and uranium, and so they give out higher radioactive response. The sandstones often quite clean and have a much lower response. Carbonates, as I said, typically show up at even cleaner response, if you like, even lower radioactivity than sandstones. And of course, once we go into the basement, in this case, I've given it quite a nice high gamma ray response again. So this is what we call a wireline log. It's a trace of a measurement made in a wellbore from which we can make various assumptions and calculations and get a feel for the types of rocks we have. So this is a crude rock typing, so if I looked at this rock, I'd say, oh yes, okay, there's a shale up here, there's a sandstone here, that looks a bit cleaner. Depending on how it drilled, I might infer that, okay, that's possibly carbonate, a carbonate cemented zone, or a limestone in its own right, and we're probably back into another sandstone here, and then I would probably say, oh, that's another shale, unless I knew from the drilling evidence that actually, yes, that's gone into hard basement.